In this video, we're going to be looking at this problem, random pick with weight. We're given an array of integers w, where wi is the weight of the ith index. So we need to implement the function pickindex, which randomly picks an index I, and the probability of picking I is wi over sum w, which is a sum of all the elements of w. So for example, if w is this array, 1, 3, you can think of this as parts of a pie. So w0 has one part, and w1 has 3 parts. So it should be clear that we should be randomly returning index 0 25% of the time, since that's 1 over 4, and returning index 1 75% of the time, since that's 3 over 4. And of course you can generalize this with multiple weights. Okay, let's break this question down. You might actually already be familiar with this concept, but essentially we're trying to implement weighted random sampling. In weighted random sampling, you have items that are weighted, and the probability of each item to be selected is determined by its relative weight. So for example, let's say that we have the objects apple, banana, and orange, each with these weights. Let's say apple gets 1, banana gets 2, and orange gets 3. Well, the sum of all the weights is 1 plus 2 plus 3 equals 6, which means that apple's relative weight is 1 over 6, banana is 2 over 6 or 1 over 3, orange is 3 over 6 or 1 over 2. So we expect apples to be selected 1/6 of the time, bananas 1/3 of the time, and oranges half of the time. In this problem, we're given the weights w, but we need the relative weights. So first let's sum the elements of w. Then we can get the relative weights by creating a new array. Let's call it A, where AI is equal to wi divided by sum w. Now the question is, how are we going to sample? We're going to be generating random numbers from 0 to 1. The question is, how do we map this random number to the probabilities of our weightings? So here we're going to use a common pattern called a cumulative sum array. In a cumulative sum array, the element at index I is equal to the sum of the elements of the other array from index 0 to I minus 1. So let's see this in action. So the weights here are going to be 1, 2, and 3. The sum, of course, is 6. The relative weights are going to be 1 over 6, 1 over 3, and 1 over 2, as we mentioned. So cumulative sum arrays start at 0. The value at index 1 in the sum array is equal to the sum of the elements from index 0 to 0 in relative, which in this case is just 1 over 6. The value at index 2 is equal to the sum of the elements from index 0 to 1 in relative, which here is 1 over 6 plus 1 over 3, which is 1 over 2. And the value at index 3 is equal to the sum from index 0 to 2 in relative, which is 1 over 6 plus 1 over 3 plus 1 over 2, which is of course 1. When we compute the cumulative sum array of the relative weights, we'll always end up with a total sum of 1. Now notice the gaps in between the elements correspond with the relative weights. So for example, between index 0 and 1 is 1 over 6. Between index 1 and 2 is, 1/2 minus 1 over 6, which is 1 over 3. Between index 2 and 3 is 1 minus 1 over 2, which is 1 over 2. So this is exactly what we need. After we generate the random number, we just need to check in the cumulative sum array between which two adjacent elements does that number fall under, and return the lesser of the two indices. This makes sense intuitively. So if we're generating random numbers between 0 and 1, for example, 50% of the time, the number is going to be greater than 0.5. So it's going to fall under this range, 1 over 2 and 1. So then we return the lesser of the two indices, which here is 2, which corresponds to orange. So lastly, how are we going to find the range, the two adjacent elements, that the random number falls under? Well, we could just linearly search through cumulative, but since cumulative is monotonically increasing, its elements are in sorted order. So instead, let's binary search through cumulative. Great, so at this point we have a working solution. Let's look at the time complexity. Well, in the pre-computation step, we're summing the elements, that's O(n), computing relative weights, that's also O(n), and computing the cumulative sum array, that's O(n). So overall, it's O(n). We also need a new array for the relative weights of size n, and cumulative sum array of size n plus 1. So the overall space complexity is O(n). For the pick weight part, we're going to use binary search on the cumulative sum array. So that's O log n. It doesn't use any additional space, so it's O(1). Let's implement the solution in Java. Let's start off by computing the cumulative sum array. As we said, we first have to compute the sum of the weights. So notice here that we're using a double. This is because later on we have to use floating point division rather than integer division. The cumulative sum array is going to be 1 larger than the weights array. And just to check that the length is greater than 0, then we can safely set the first value to be 0. Let's make a for loop. So let's combine the computing the relative weights and computing the cumulative sum array in one step. We can do this by setting the value of cumulative at index I to be the value at index I minus 1 plus W I minus 1 divided by the sum. Take a minute to understand this. This is just to combine these two steps. So we're computing the relative sum here, and then we're adding it onto the previous value in the cumulative array. This is so that we can compute it in one step. Now let's work on the pick index method. So let's first handle the edge case of when the cumulative sum array's length is less than or equal to 2. So when the length is 2, we know that there's only going to be two elements, 0 and 1. So we return 0. If the length is 1 or 0, then it's technically invalid, but we're just going to return 0 here. Next, let's generate the random number. So we're going to be using the random class. And now let's implement binary search. Keep in mind this is the way that we're going to be computing the mid index rather than just simply high minus low divided by 2. This is to avoid integer overflow. This is a pretty standard pattern for binary search. Definitely take the time to memorize this because it'll be really useful to use this during interviews. Typically, at this point, we would return low, but keep in mind, the cumulative sum array's length is 1 larger than the weights array. So we actually need to return low minus 1. Okay, let's run this. And you'll see that it passes. And that's how you solve this problem, random pick with weight.